All right, good morning, everyone, and howdy. Welcome to our final pass to publication for the semester. I am so excited to introduce today's host and spend the morning learning with y'all. Again, this is our last pass to publication for the semester, and we're so excited that all of you get to attend and be with us this morning. All right, let's get started. Today, we have Dr. Chuck Huber presenting Introduction to Multilevel and Longitudinal Data. Chuck Huber is the Director of Statistical Outreach at StataCorp and an adjunct associate professor of biostatistics at the Texas A&M School of Public Health and the New York University School of Global Public Health. He produces instructional videos for the Stata YouTube channel, writes blog entries, develops online net courses, and gives talks about Stata to conferences and universities. He's published in the areas of neurology, human and animal genetics, alcohol and drug abuse prevention, nutrition, and birth defects. Dr. Huber currently teaches survey sampling at NYU and introductory biostatistics at Texas A&M, and he's previously taught categorical data analysis, survey data analysis, and statistical genetics. Welcome, Dr. Huber. We are so excited to learn from you today. And with that, I'm going to hand it over to you.
Sorry, had my voice muted.
Can
So
you
thanks,
hear me?
Jordan. Yeah,
Dr. Huber,
yes.
hi. Hi, thank you so much for being with us today.
Oh, my pleasure. Thanks for having
We're
me.
so excited. I have to tell them the story about my work with your family.
Okay, sure, go ahead.
So, um, so when I started at university, um, Dr. Huber's father was my department head. And he was a mathematical genius, just like Dr. Huber is, and here, Dr. Chuck Huber. And so, and he was the nicest man. He was always so kind and generous to me. So I have to thank you, Dr. Huber, for sharing him with
Oh, well,
me.
thank you.
And we are so glad that you're here to share with our graduate students and faculty about this multi-level longitudinal data information. And thank you so very much. We
Oh, well, thank
appreciate
you.
it.
Thanks
And
for,
I'm in a meeting at the graduate school. I'm going to jump off for just a minute. I'm going to try to get back on. But I wanted to say hello and thank you.
oh,
And
well,
thank you.
thank you. That's very kind of you to say that.
Yes,
So,
yes. Thank you, Jordan, for introducing.
No problem. Thanks for sharing, and let's get started.
okay, so let me share my slides here. And I'll show you the outline in just a moment. So we're going to be talking about multi-level and longitudinal models today, and how to model these kinds of data. You can download all the materials for today at this website. It's tinyurl.com/multilevel behavioral. It has all the slides, the data sets, the do files. There are some fun tricks in the do files in here. Some of the graphs you'll see, you may scratch your head and say, well, how did he do that? Well, I don't have all the code in the slides, but all the code is in the do files. So if you want to see how to make some of these slides, all of that is available here at this tiny URL. I pasted this link into the comments window earlier, so you can just click on that link, and I'll have this link at the end as well. Okay, so here's the outline of what we're going to talk about today. We will probably make it through fixed versus random. This talk can actually run anywhere from 90 minutes to 2 hours if I do the full thing. And I thought about cutting some of the parts out, but I thought, well, I'll leave it in, and then if other people want to look at this later on, you'll have the material there. But I will probably make it through fixed versus random this morning, and then we'll take questions. I do want to acknowledge someone you're probably familiar with if you're in EdPsych. His name is Yuri Bronfenbrenner, and he was not a statistician, and he did not really work in multi-level modeling per se as a statistician, but he's often credited with being sort of the founder of the idea of multi-level models, or what people often call the ecological model of human development. He was born in Moscow in 1917, died in Ithaca, New York in 2005. He was a professor of psychology at Cornell, and he's most noted in the United States as being the founder of the Head Start program here in the United States. But in the research world, he's most often remembered for developing this ecological model of human development. And the idea is that individual people have certain characteristics about them, such as their age, sex, their health, and things like that. But people don't develop in isolation. They develop in a context. And he sort of systematically defined this as being kind of a microsystem immediately around the individual, your family, your school, your church, your peers, and things like that. And then a mesosystem around that, and then an exosystem around that, maybe your neighborhood, the media, things like that. And then a macro system that includes things like your overall culture and attitudes and ideology. The reason I mention this is because this is the intellectual idea that gives us multi-level modeling, and so that's what we're doing with multi-level modeling, is we're going to try to take into account these contextual factors around the individuals that can also have an effect. So that's the idea behind what we're going to be doing today. Longitudinal is a little bit different, and we're going to cover that as well. But that's kind of where this idea comes from. I'm going to be using a simulated data set today, and it consists of repeated observations of test scores on adolescents from ages 14 through 18. And I can't emphasize this enough. This is completely fake. It's simulated data. But that's the idea. We have repeated measurements on test scores from ages 14 to 18. So the repeated observations are nested within students. We have multiple observations per student, and then the students themselves are nested within teachers' classrooms. And we'll talk more about the implications of that here shortly from a statistical point of view. This is the simulated data set. It's included in that download. It's just called tests.dta. And it includes the following variables. So I have teacher, which is the teacher's ID, student, which is a student ID, and then I have age, which is measured in years. C age, it looks like cage, but I call it C age. It's centered age, and we'll come back to centered age, what that's for shortly. Sex is just whether the student is male or female. Score is the student's test score, ranging from 0 to 100. It's continuous. Pass is an indicator variable for whether or not the student passed. So whether or not the student had a score of 70 or higher. And then experience is the teacher's years of experience, and 0 is a variable I needed in here just for some of the graphs, so it's kind of a nonsense variable. So let's list some of the raw data just to get to know the data. So if I were to list the first 10 observations, I've put them in two groups of 5 because the first 5 observations are all from the same student. So the top box here are all data for student 68. Student 68 is in teacher 3's classroom. Okay, so keep in mind all the first 5 observations are from student 68. So the 5 observations were measured at ages 14 through 18 for student 68. So 14, 15, 16, 17, and 18. Now, centered age, what I've done with C age here, or centered age, what I've done is taken the midpoint of age, which is 16, and defined it to be 0. So then age 17 is 1 year beyond 16, and age 18 would be 2 years beyond age 16. Age 15 would be 1 year prior to age 16, minus 2 is 2 years, or 14 would be 2 years prior to age 16. So all I've done is converted 14 through 18 to minus 2 through 2, and I'll show you why we're doing that here shortly when we look at a graph. Sex is labeled in here. The scores are the raw test scores, again, between 0 and 100, and then I have the teacher's experience here. You can tell that I made a mistake when I simulated the data because if the student at age 14, the teacher had 8 years of experience, experience should have incremented along here, and I forgot to do that years ago when I created the simulated data. But that's not terribly important for our purposes. The bottom 5 observations are for student 69, so it's the same pattern. I have 5 repeated observations for student 69, who is also nested within teacher 3's classroom. So that's what the raw data look like if you were to list it. If I were to look at a summary statistics for these variables, I can see that there are 375 students. We'll come back to the number of teachers later. The main thing I'm looking for here is the number of observations, and I don't have any missing data. And that's the main thing I look at when I do these summaries is which variables have any missing data if they do. This is simulated data, so why make my life difficult? I simulated complete data, so we don't have to deal with multiple imputation or anything like that. Another thing I like to do with a new data set is I like to skim down the min and the max column to look for odd, strange values. So, for instance, age, the minimum is 14 and the maximum is 18, and that's how it should be. If I had a minimum age of 0, that would make me scratch my head and take a closer look at why are some of the ages 0. But we have simulated data, so it's nice and clean. Another thing that I like to do before I start building statistical models of data is graph the raw data to get a feel for what the data looks like. I often think that statisticians are a bit like painters. If you're a painter and you want to paint someone's portrait, you need to take a good look at the person you're painting before you start painting their portrait. And to some extent, statisticians are painters of data. We take data and we need to look at that data carefully and then build a model, some sort of a statistical representation of the characteristics of that data. And you can't really do that if you haven't taken a good look at the raw data to look at the patterns there, because after all, the model should fit the data, not the other way around. Okay. So one of the features here, what I've done is some people call these spaghetti plots. They are the trajectories of individual students 60 through 69. If I plotted everyone, it would make a mess and you couldn't see any patterns. But here I have students 60 through 69, and I have their test scores uh, plotted as line plots from age 14 to 18. So the horizontal axis is age, the vertical axis is test score. And I can see that there is noise, there is some fluctuation, but they tend to have an upward trend to them. If you sort of squint your eyes, there is a kind of upward linear trend to these lines. And so a good old-fashioned linear model should work well for these. Ideally, in the real world, you would want to plot other plots for, say, students 70 to 79 and 80 to 89, just to get a feel for all of them, but or draw a random sample or something like that. But this just gives us some idea of what the raw data look like. Okay? So let's talk about single level models first. That seems a little weird, but this allows us to establish some concepts and notation. So I'm going to use the letter Y to denote the dependent variable or outcome variable, fairly standard. And I'm going to use the index I or the subscript I to index student. So YI refers to the ith, the yth outcome for the ith student. Okay, outcome Y for the ith student. So if I were to imagine these little red boxes here are the outcomes for each student, the test scores, what I'm going to assume in the beginning is that all of the observations, the test scores, are independent of each other. What the score for one student has nothing to do with the score for another student. I'm going to treat them all as completely independent of each other. So if I were to draw a picture of these, so I just plot the test scores along a line plot here, and I could plot the mean at some point. So let's say the mean mu appears somewhere along this line. I can describe any observation in the data set, any yi, as a combination of two numbers. The mean, which I'm using the Greek letter mu here, so mu plus the deviation of that observation from the overall mean. Okay, so that's going to be EI or the errors or the residuals. So all I've really done is taken each observation and described it using two pieces, an overall mean and a deviation from that mean. Okay, so it's a very, very simple kind of silly linear model. Jargon-wise, we often refer to the left side as the observed part. That's the observed data. The mu or the mean is going to be the fixed part of the model. And then the random part, E, I, that's random because it's different for each person. The mean is going to be the same for everyone. But the random part, how much they deviate from that mean, is going to be random, and it's unique to each observation in the data set. Okay, so observed, fixed, and random. We can then talk about the distribution of those error terms. So if we were to take just the error terms, that part of the model, and we were to plot them on a line plot, they would roughly have a normal distribution. This is fairly typical, and because we've already accounted for the mean, we would say that the mean of the errors is going to be 0 because it's distributed about that mean. So the mean, once you remove the mean, the distribution for the errors is assumed to be normally distributed with a mean of 0 and some variance. We could estimate the variability of those error terms about the mean. Okay? So that's one of the assumptions that we're going to make in building these models. So that's a single level model. Kind of silly, but it's a good starting point. Now let's talk about two level models. So let's say that we account for the fact that these students are nested within classrooms, and each classroom has a different teacher. Well, it may be that certain teachers have more experience or they're just naturally better teachers or whatever, but there could be teacher level effects that affect all of the students in their classroom. So there's going to be natural variability of each student on the test scores, but there may be a teacher effect that sort of either lifts or lowers, on average, a little bit, the scores of the students within a particular teacher's classroom. And so they may be correlated. Students' test scores may be to some degree correlated, and we would like to account for that when we build our model. So what we can do, we can refer to the teacher level as level 2 and the individual students as level 1. So we're going to start labeling our nesting structure from the bottom up. Level 1 is students, level 2 are teachers. And then we also need some sort of subscript to keep track of these. So I'm going to refer to the Y's using two subscripts now, I and J. So J represents the student or indexes student, and I indexes the teachers. Okay. Now, the student observations will vary about each teacher's classroom mean. So we could estimate the mean test score in each student's class and each teacher's classroom. And each student within the classroom will deviate about that classroom mean. But then we can think about each of those classrooms, and those classroom means deviate around the overall grand mean of the entire data set or the entire school. So what we can then do is we can take a particular observation, Yij, and we can break it down into three pieces now. We still have our overall grand mean, but that student's observation now deviates from the classroom mean by this Eij amount. So how far does the observation deviate from the classroom mean or the teacher's mean? And then we can ask the question, how far does the teacher classroom mean deviate from the overall grand mean? One of the things that I want to emphasize here is that that residual is exactly the same distance as it was before. So when we only considered this to be a one-level model, that distance is exactly the same. All we've done is broken it into two pieces, and we've broken it into two pieces based on the deviation from the observation to the classroom mean and the classroom mean to the grand mean. Another thing to notice here is that E has two subscripts, I and J, because we're referring to each individual. But the U, this green arrow distance, that is the distance from each classroom mean to the grand mean. Well, because I'm only taking into account each classroom mean, I only need the index I. I don't need the J's because I don't have a separate U for each student. And so what I'm going to do then is refer to this as UI dot. The dot just reminds me that there is a J in the data set, the students, but I don't need it for the UIs. It's just the distance between the teacher mean and the grand mean. So again, for a two-level model, all I've done is taken the same observation and broken it into three pieces: the grand mean, the distance from the mean to the teacher mean, and then the distance from the teacher mean to the observation. Okay? So again, we have the observation on the left side of the equation. The fixed part stayed the same. That's just this mu. And then I have the random part becoming more complex. Now I have two error terms. I have ui dot and I have eij. I'm going to make the same assumption about the ui dots that I did before. Both of them, I'm going to assume both have normal distributions with a mean of 0, and I'm going to estimate separate variances for each of those. Okay? So that's two-level models. That's kind of the basics of that. Now let's talk about longitudinal models. So if I go back through again and talk about observations, now the red dots represent the repeated observations within students. So remember, I have test scores at age 14, 15, 16, and so forth. Each of those red dots represents a test score at a different age, and the green boxes now represent students. So the repeated observations are nested within students, and because they are all reported from the same student, they're almost certainly correlated. Unless the students are just randomly guessing on the tests, the same student taking the same test is probably going to be correlated. So we will go back through this again and refer to level 1 as the repeated observations. Level 2 is now the students, and I can index these just like I did before, except that I'm going to change to the letter T just for fun to remind us that T is like time. So I have the teeth observation measured on the ith student. Okay. So now student is the second level and the repeated observation is the first level. What I could do is calculate a mean within each student because I have repeated observations within each student. I can calculate a mean for each student, and then I can talk about the deviation of each of those observations from the student's mean. And then I could talk about each student's mean deviating from the overall grand mean. So then I can take each observation and talk about the deviation of that observation from the student mean from the overall grand mean. And at this point, you're probably scratching your head and thinking, it looks like he just copied and pasted those slides, and all he did was change the letter E to J to T. This looks exactly the same. And you'd be right. I did, in fact, copy the slides. And that's important. For or for longitudinal data, up to this point, the concepts in the math are identical. It's the same concept if you have longitudinal data or two-level data. But what makes longitudinal level a little different is the ordering of the data. When we talk about kids within classrooms, they're exchangeable. There's no natural ordering to them. But if I have repeated observations within a student, those come with a natural ordering, and I'd like to take that into account. So what I'm going to do is I'm going to take this slide, this graph right here, and I'm not going to change anything about it other than I'm going to flip it up on its side. Okay. So now I have that same plot. The observation deviates from the student mean deviates from the grand mean. The equation stayed the same. Nothing has changed other than it's sideways now. But now let's start making some additional changes. Let's add a horizontal axis to this. So now our previous graph is the vertical axis. I have an age axis ranging from age 14 to 18. And I'm going to extend these means out into the plot. So I'm going to refer to the overall mean, this grand mean, as the grand mean. And I'm going to extend the line for the student mean out into the graph as well. But notice that they're flat because I'm not taking anything about age into account in my model. So it's just a grand mean. So let's start changing some other things. Let's change the overall mean to beta 0. Let's start thinking in terms of linear regression. So B0 would be the intercept for a linear model. Now it's still the same, it's flat because we're not taking age into account, so the math hasn't really changed. It's only the label B0 that's changed. But maybe we'd like to allow for change over time by including age in the model, and that allows us then to have a beta 1 term, which is a slope. So now we have both an intercept and a slope. So this means that the test scores could increase over time, they could decrease over time. But by adding age to the model and having this beta 1, that allows the model to take into account that it's not just a flat mean anymore, it's actually a slope or a regression line. But the rest of this hasn't changed. We still have EIT and UI dot in here. Conceptually, it's still the same. We've just made the fixed part of the model a little bit more sophisticated to allow for change over age. And that's what makes it longitudinal. Okay, by adding in this age piece, it's not just a fixed mean anymore. There's a little regression line there. Now, to make this even more sophisticated, what we could do is imagine plotting just the dots for a single student. Okay, that student mean here, that green line is an average over all students for now. But let's take a look at those dots for a specific student. We might look at that cloud of points and say, that green line doesn't fit as well as it could. If we allowed for a little bit more slope, we could fit a better line just for that one particular student. And that would be very hard to do manually, but with computers, this is very easy to do. What we can do is fit a separate slope, a separate regression line for every student in the data set. And in fact, that's what we're going to do. So we're going to add another random term to our model here. So now we have U0 I dot and we have U1 I dot. What this is if we look at the left-hand side, beta 0 plus beta 1 age is essentially the average slope or the average regression line for everyone in the data set. And then what I'm going to do with U0 I dot plus U1 I dot age, that's like fitting a separate regression line for every person in the data set. So I have an average regression line and a unique regression line to everyone in the data set. And then I can talk about the deviation of each individual observation from that individualized regression line. Okay? So that's what I'm going to do with this brown line here. I'm going to fit a separate regression line for every person in the data set. So now that equation's getting pretty large, let's take a look at what each of those error terms are referring to. So we have our overall averaged regression line here. That's the beta 0 plus beta 1 year. And then we have a deviation of the intercept for the student, and that's going to be this U0 I dot. So that's a certain deviation away from the average regression line. But notice it's parallel because it doesn't take age into account yet. Then I have this brown line here labeled U1I dot, and then it has age next to it. Well, why does it have age next to it? Well, that distance is a function of age. The distance or the length of that brown arrow is a function of age. So it depends on where I am on the age axis. If I were to shift over here to say age 16 in the middle of the age axis, that arrow would be zero. It would have zero length because it's the two lines overlap. If I went further to the left, say over here at age 14, that arrow would actually be negative because that point on the age axis, the brown arrow would be pointing down, or the distance between the green line and the brown line would be negative. And that's why we say it's a function of age, because the length of that brown arrow depends on where we are on the age axis. Okay. And then the red line, EIT, that's just the deviation from the individual observation from that unique regression line for each person. Okay. So that's kind of the concept. Now our model's looking kind of bigger and more complex, but we're still going to make the same assumptions. We're going to assume that each of those error terms is normally distributed with a mean of 0, and we're going to estimate the variability of each of those error terms. And the software will do that for us later. Now let's take it one step further. Let's talk about three-step models. So now let's take into account all the features in our data set. Recall that we have repeated observations nested within students, but those students are also nested within teachers' classrooms. So we would like to take all of the possible correlation or relationships into account in our model. So what we can do here is we can assume that we could calculate a mean for each student and talk about the deviation of the repeated observations from the student mean. Then we can talk about the student means deviating from their overall classroom mean. So now the blue hump here, the blue normal distribution, represents the distribution of student means within the classroom. So blue is classroom, green is individuals. And we can talk about the deviation of the classroom means from the overall grand mean, or the teacher means from the grand mean. So there are now three sources of variability here. Well, two, level 1 to level 2 and level 2 to level 3. So again, we're going to use this level terminology. So level 1 is repeated observation, level 2 is the students, and level 3 are the teachers or classrooms. We again need to index these. So now I'm going to refer to YIJK. So that's the yth outcome for the kth observation within the jth student within the ith teacher. Oh, excuse me. Now this starts to look messy, and this is one of the things that's very intimidating when you open a book about multi-level models, is you see a lot of these subscripts. Don't get too obsessed about the subscripts. They're only there to help you keep track of which observation goes with, or which outcome goes with each observation time, which student and which teacher. It's just an accounting tool. Okay, so now the observed part is the same. We have the YIJKs. The fixed part for now we're going to leave as mu. Now we have three of these random deviations or random effects in here. So what does this mean? Well, now if I talk about a particular observation, I can refer to or talk about this observation deviating from the student mean. So that's one of the repeated observations within student. So this red line, or EIJK, is the deviation of the observation from the individual student's mean. And then the green arrow, UIJ dot, that green arrow length is the deviation of the student's mean from their particular classroom mean. And then the blue line here labeled UI dot dot, that's the deviation of the classroom mean or teacher mean from the overall grand mean. So what I will have effectively done with this kind of a model is I've taken the observation and partitioned it into four parts: the overall grand mean, the deviation of the classroom or teacher mean from the grand mean, plus the deviation of the student mean from the teacher mean, plus the deviation of that particular observation from the student mean. Okay? So that's all we're doing with these models. And it's the same residual. If we ignored the clustering, that residual would be the same length overall. So we're not changing the data in any way. All we're doing is splitting one big residual into three residuals, and we're chopping it up based on these various cluster means of the various clusters. Okay, same assumptions as we had before: normally distributed, mean of 0, estimate the variance for each one. But now if we flip it on its side like we did before, we're going to extend the means out into the age axis here, just like we did before. But now we have three of these. We have a grand mean, a teacher mean, and a student mean. We're going to change the mu to a beta 0, just like we did before. Then we're going to add an age term in here in order to allow for slope of these. We're also going to imagine that cloud of points again and say, well, we could fit a better line to that cloud of points. So let's fit a custom regression line for each of the students in the data set. And now we have four of these deviations, just like we did before, but we have an additional, this blue line here. So we have our average regression line, beta 0 plus beta 1 year. Then we have the deviation of the teacher, a particular teacher's mean from that line. That's the blue UI dot dot arrow here. Then we have the green arrow, which is the deviation from the teacher mean to the student mean. That's the U0IJ dot. Then we have that brown line again, which is depends on where we are on the age axis. That's the random slope. We refer to that as a random slope. And then we have the deviation of the observation from that unique regression line for each student. So now we have four of these random effects, and we're going to make that same assumption. They're all normally distributed with a mean of 0, and we're going to estimate the variance for each of those. Okay? So that's the general idea. The question then becomes, well, how do we do this in practice? And in particular, how are we going to do this with Stata? So let's start here. Rather than backing all the way out to single level models, let's start with just this 3-level model. So I have the overall grand mean, a teacher mean, and a student mean. How am I going to do that? Well, let's take that equation, and I've color coded this to hopefully make the math and the output match up a little bit here. What I'm going to do is I'm going to type mixed. So the command I would use in Stata is called mixed. The dependent variable is score. That's the student's test scores. And then I need to tell Stata about the nesting structure of the data. So I have teacher first. I have two vertical lines, and then teacher. That's the top level of nesting, and I need that little colon in there. And then I have two vertical bars again, and then student colon. So that describes the nesting structure, and the order is important here. Student is nested within teacher, and it's assumed that all the observations then are nested within student. We don't have to put an observation nesting level in here. Then I also have comma stddev. By default, Stata reports the random effects, those variances, as variances, but I've never been very good at thinking on a squared term. Variance does not have an intuitive interpretation to me, whereas standard deviation does. The square root of the variance is the standard deviation, and Stata will report these as standard deviations. And I know how to interpret those because they're on the same scale as the original data. So let's look at the four parts here. Underscore cons, that's Stata's way of labeling the intercept for the model, and it's 68.7. That underscore cons is this beta 0. That's the intercept. So we would say that the average test score in our sample here is 68.7. The average test score is 68.7. But then we have all these random parts, these error terms hanging off the end here. So what are those, and where are they in the output, and how do we interpret them? Well, the blue number, that's the standard deviation for the observation, the individual. How much does each individual deviate from their particular classroom mean? Now, remember, this is on a test score scale. So this 0.83 means that there's about a 0.83 test score deviation of each person's mean each classroom mean around the grand mean. Okay. So there's not a lot of variability at the teacher level, at the classroom level. Less than 1 point deviation from the teacher classroom means to the overall grand mean. Then the green line here that says student identity, that green number 4.94, that's the deviation of each individual from their particular classroom mean. So notice it's about 5. So that's a half a letter grade, right? If this was a 0 to 100 test score, 4.9 is about 5. So that's about a 5-point deviation around the classroom mean. So there's a lot more variability at the individual level. And then the red number here, that's the deviation of each observation from repeated observation from that individual's test score mean. Okay. So let's make this a little more concrete. Let's go back and look at student 69. And let's take what we've learned from our model to fill in some things here. So if I take student 69, I have their repeated observations from age 14 to 18. I know that the grand mean is 68.71. I got that from my output here. Remember, the grand mean is 68.7. And then I also can use the predict statement in Stata. This is all in the do file, but I can predict what is UI dot dot for that particular classroom, for teacher three's classroom. And that's zero point 0.7. Okay, so for teacher three, every student in teacher three's classroom gets a zero point 0.7 bonus point for being in student three's classroom for whatever reason, teacher experience, better teaching methods, or whatever. And then we have the student effect, which in this case, the student effect is 3.78. So student 69 is getting 3.78 bonus points for being student 69. For whatever reason, they tend to do, on average, a little better than their peers within that particular teacher's classroom. So that student, and notice the teacher effect and the student effect are the same for all 5 observations because it's the same teacher across all 5 observations and it's the same student across all 5 observations. So those are the same within teacher and within student. Now the residuals, that's how far off is each particular repeated observation from the student mean. And those are different for each observation because they're taken at each age. So we have at age 14, the student did minus 6.18 points lower than their average than the average of all 5 of their test scores. Same thing at age 15, they did a little worse. Let's take a look at the last observation at age 18. Here they scored 9.82 points above that student's average. Okay, so they were better by the end. So now what happens if we add those numbers together? If I were to take 68.71, the grand mean, plus the teacher effect, 0.7, plus the student effect, 3.78, plus the residual for that particular observation, I get 83.01. What is 83.01? That's 83. That's their test score. So again, what I've done is I've partitioned up their observed test score into 4 parts. The overall mean, a teacher effect, a student effect, and then a deviation from that number. Okay. So we could also represent this graphically. So let's graph that particular student's scores, the red dots here. So the red dots are the actual test scores, the observations. The black line here is the overall mean for the entire sample. The blue line represents the average for teacher three's mean. That's the average in teacher three's classroom. The green line represents the average test score for student 69 across all 5 ages. That's the average test score for student 69. And then if we look at those red dots, we can see that this model does not fit the data very well at all, right? Because there's kind of an obvious upward slope to those red dots. So what we ideally should do is fit a better model. We need to allow for slope in this model. So that's what we're going to do next. We're going to add age as a fixed part of the model. Rather than adding age, I'm going to add C age, and that allows the lines to cross in the middle. Remember earlier when we were looking at these lines here with age, it's easier to see them cross in the middle than to cross somewhere outside of the age axis. So I'm going to use centered age. It looks like cage. So if I add centered age to the regression model here, I've added C age to the fixed part over here on the left. Now I can see that the intercept is the same, 68.7, and I've allowed for an upward slope of about 2.3 test score points per year. So each additional year of age is associated with a test score that's 2.3 points higher than the previous year. And then if I look at the random parts at the bottom, notice that the teacher random effect hasn't really changed. It's still about 0.83. The student part now has 2 pieces. So the green part, that's the up-down, the vertical deviation of each observation, of each student's mean from the classroom mean. And then the SD age, that brown 1.87, that represents the variability of the slopes. Not the vertical up-down of the line, but what's the deviation of the slopes, the angle of that line. So we have 2 sources of variability there. And then the very bottom, the red line that's the red deviation, standard deviation of 2.1, notice that's gone down. It was about 5 before, and now it's down to about 2. The reason for that is if we take a look at this brown line, well, first off, we've allowed everything to have slope to it now. Even the black line has a slope to it. And we have also, oh, did I skip too far ahead? I did skip too far ahead. I'm sorry. This is we've added age and whoops, we have just the single green number here, the single green standard deviation, and then the red number at the bottom, the individual observation standard deviation has reduced to 3.6. And that's because we've allowed for slope here. And so that slope allows the lines to fit the red dots better. Okay, sorry, I skipped too far ahead earlier. Too many slides. So here, what we want to do is fit a separate regression line for each student. We can do that by not only adding C age to the fixed part of the model over here after mixed, so mixed score C age. I'm also going to include C age next to student. And what that's going to do is fit a separate slope or a separate regression line for every student in the data set. Okay. And so that's where we get the separate, the vertical deviation of 5.37 and the slope deviation of 1.87. Okay. And if we were to plot this for student 69, this is the raw data for student 69 and each of the lines. The black line again is the overall grand mean or grand regression line. The blue line is the teacher mean. The green line is the unique mean for student 69. And then the brown line allows for a random slope that's particular to student 69. Now look at how closely that brown line tracks those red dots. And in fact, that's the best we can do. Unless we start fitting curves, we could add a squared term or a cubic term. We could get it even closer, but then the model becomes unnecessarily complex. So what we've done for student 69 and every other student in the model is fit a custom regression line for that individual's cloud of points. So this fits very well, and that's why when we look at the residuals, the observation level residuals are now much smaller. Okay, the teacher error standard deviation that didn't drop much. The student level variability that didn't drop much, but the residuals at the observation level, because those lines fit so much better, those deviations and that standard deviation have dropped even more. What we can do then after we fit this model is we can use state as margins and margins plot commands to graph an overall trend line for this data set. But what it also includes is a confidence interval around each of those points. And that confidence interval accounts for all of the correlation and all of these different standard deviations at different levels. These are the confidence intervals are estimated correctly, accounting for all the features and nesting in our data set. Okay. Now, often you will see people who come from a policy background or a economics background. They'll talk about cluster robust standard errors, and we could do this, but it doesn't actually estimate the variability at each level. It simply accounts for it in a mathematically different way. If we do this, we get essentially the same results. The standard errors will be different, so the confidence intervals will be a little wider or narrower depending on which method we use. But the fixed part, the actual coefficients will be the same. And in this case, the p-values are all very small, so it doesn't make a big difference which method that we use. Okay. You can, if you want, estimate something called the intraclass correlation coefficient. I've never liked this term because it isn't a correlation. Mathematically, if you look at the math, this is simply the proportion of variability at each level. So at the teacher level, only about 2% of the variability in test scores is at the teacher level. About 87%, if you round it, about 87% of the variability in student test scores is at the student level nested within teacher. So most of the test score variability is due to students, not due to teachers, which is not something we account for when we talk about policy cures to improve test scores. Anyway, so we are right at 10:45, and so I think I'll actually stop here and take any questions. And if we don't have any questions, I'll jump back in and talk about fixed versus random. But I want to leave plenty of time for questions. So let me stop sharing. Are there any questions at this point?
Awesome. Yes, please drop your questions in the chat if you have any. And if I don't see any questions here in the next minute or so, then we will continue with fixed versus random. I just have to say, while I'm giving y'all time to put your questions in, visually, I've never seen it presented like that in my classes. And that really clicked for me when I was taking my advanced statistics classes. I did not understand what all the little differences in the variances are at the end and
Yeah.
how they fit into this equation. I didn't understand the equation in essence and what it was telling me. I didn't know how to read it. And so seeing it visually, how you laid out, has really not only like refreshed me in multi-level, but has given me a deeper understanding because I could write the equation correctly for class assignments and stuff, but if you asked me
Yeah.
to explain it, I wouldn't have been able to. I'm not saying I could do that after this, but I understand what's happening now, and given a little time, I think I could be able to explain it to others.
Yeah.
So maybe that was just me, guys, but that was extremely helpful visually for me.
Oh, well,
I'm
thank you.
looking, I see some feedback in the chat saying this was really helpful, but I don't see many questions, so I'll give it another few seconds. I'll take a sip of my soda, and if I don't see any more, then let's go ahead and do the fixed.
Okay. Yeah, thanks. These slides are about 20 years old now, and they came about because I was teaching. I wanted to cover multi-level models in my Intro to Biostat 2 class. But that's a fairly basic course. It's only second semester of Intro to Statistics, but it's such an important feature of data sets these days. And I needed a way to explain it to students who would normally be kind of scared off by these things. So I remember vividly about 20 years ago sitting at my kitchen table thinking, how can I draw a picture of this? And so I literally just started drawing pictures of those equations. I'd say, well, what does this part mean? And what does that part mean? And that's how the slides came about. And
That is
so,
what I needed. Like, that
yeah.
was, I had not seen that in any of my courses. I do have a question, but it's specific to if this was a class, which one would it be at TAMU? Now, there's lots of different departments. There's like statistics departments, different mathematical departments, and then some departments like Ed Psych or different departments have kind of their in-house statisticians. So I can only really speak for like Ed Psych and maybe TLAC in the College of Education, but I want to say for us it was Dr. Kwok and
Oh,
Mohammed Taheri is, yes, is on here as well. And I believe he took that class with me. Multi-level we took with Dr. Kwok, correct, Mohammed?
Yes, that's correct.
Yes. So in Ed Psych, that would be multi-level modeling with Dr. Oyman Kwok.
yes.
Um, His class was great too. He's an amazing statistician, but I think for me, what clicked here that was different from his was the visuals. So I feel like if you took that class and had this like download these slides in the back end to help you, you would be set for that class because that's what I needed in that class. And if that was the only question, we have about 10, 11 more minutes. I think we can go ahead and continue, Dr. Huber. I'm fully with you and have followed everything you've said thus far.
Okay, good. I'm glad. I am doing this. You asked about other classes. Karen, and
Mhm.
I'm not clear on her last name. Karen Rambo Hernandez. Her husband Paul
Yes.
also teaches at
That's
EdSci.
right.
Yeah, and I'm doing this guest lecture for her in a couple or 3 weeks, right after Thanksgiving, I think. So I do this as a guest lecture for her multi-level modeling course. Um, this is also up on our YouTube channel, not to do too many stata plugs, but this video of this conceptual introduction is up on our YouTube channel. And like I said, you
Beautiful.
can download the slides and feel free to use them. I've done this lecture off and on for 20 years all over the place. And I've had professors send me these where they put these slides in their class slides. So, yeah, use them. The goal here is to get the information out. I don't care about copyrights or any of that stuff. Use them and teach with them and do whatever you like with them.
Well, we can tell they've been well developed.
Well, thank you. Okay, so let's go back then if we have a little extra time, and
Sure.
please stop me if I start running over time. So one of the questions that I get most often is, well, how do I know when to use a fixed versus random effect, and what do those terms even mean? So the way I described each of these levels, I'm talking about them as a random effect in the sense that it's random that the value is different for each observation. So the EIJK, that's going to be different for every observation. The Uij dot, that's going to be different for every student because each student is going to have their own deviation and so forth. So anytime I'm estimating a variance or a standard deviation of one of those things, that's a random effect. But let's think of another way to talk about this. What I could do, I didn't mention this explicitly, but I only have three teachers in this data set. And if I said, hey, go estimate the standard deviation of test scores, you would definitely sample more than three people, right? But this happens a lot with multi-level models, and there have been papers written about this where people will have three or four or five top-level clusters, and they will report a variance of this. Let me rewind a bit here. Where did it go? In my output. Here we go. So this top level output, this blue 0.834, that standard deviation is estimated using three classroom means. There are only three data points used to estimate that standard deviation. And that's why you see this enormous confidence interval from 0.09 to 7.41, because that's based on three people. You would never estimate a standard deviation using three observations. No one would do that. But we just did. And that happens a lot where people are doing this and they don't stop and think, oh, yeah, I only have five classrooms or four classrooms at the top. And so ideally, you really shouldn't be doing that. So another way of doing this is to treat teacher as a fixed effect. Move it from the random part. So rather than estimating the deviation of each teacher mean from the overall mean, just estimate the mean of each teacher. So now I don't have a grand mean. What I'm going to do is skip the grand mean part, and I'm going to estimate a beta 1. So what's the mean in teacher 1's classroom? What's the mean in teacher 2's classroom? And what's the mean in teacher 3's classroom? And the rest of the model stays the same. I can still talk about the deviation of the observation from the student mean and the student mean from their particular teacher mean. But the rest of the model is just different in the sense that I'm treating teacher as those three teachers are each getting their own mean. So if you think about it in terms of indicator variables, I'm talking about the graph at the top shows deviations from teacher two's mean. Well, if I wrote that here at the bottom, it would be beta 1 times 0, because this is not teacher 1, beta 2 times 1, because it is teacher 2, plus beta 3 times 0, because it's not teacher 3, plus those deviations. And so that's what I mean by treating it as a fixed effect. Okay, so I've moved teacher from the random part over to the fixed part. I'm going to actually estimate those means for each teacher's classroom. Now, here's something really interesting to notice. And it's obvious if you think about it, and I should write it out a little bit more explicitly, but if you were to treat teacher as a fixed effect at the top, I'm going to estimate beta 1, beta 2, and beta 3. But if I treat it as a random effect, I'm going to estimate one overall grand mean, and then the UI dot dots are the deviation of each teacher mean from the grand mean. But what would happen? I never did create a slide to show this explicitly, but imagine if I take the overall mean plus the deviation for teacher 1, what do I get? I get beta 1, right? Because the grand mean plus the deviation for teacher 1 is the mean for teacher 1. If I took the grand mean plus the U2 dot dot, the deviation for teacher 2, what do I get if I add those two together? Well, I get beta 2. And then if I take U3 dot dot and add that to the grand mean, what do I get? Beta 3. Mathematically, they're the same. You get the same, it's exactly the same. It's just a different way of writing it. And the output looks different. So if I treat teacher as a random effect, I get a standard deviation in the bottom of the output for how much are each of the teacher classroom means deviating from the fixed mean. So it's a random, I'm estimating a standard deviation. And I get one line if I use margins. But what if I treat teacher as a fixed effect? So I get rid of the grand mean and I estimate a separate mean for each teacher. Now in the top of the output, the fixed part of the model, I get three separate means. I get the mean test score in teacher 1's classroom, the mean score for teacher 2's classroom, and the mean for teacher 3's classroom. And then I don't get a standard deviation in the random effects parameters because I've moved teacher from being a random part of the model to being a fixed part of the model. Now, in this particular example, this makes a lot more sense because it just doesn't make sense to estimate a standard deviation or a variance using three classrooms. The other thing I like about this is now I can see the mean in each of the teacher's classrooms, And I can see that teacher 2 had the lowest mean and teacher 3 had the highest mean. And that might be useful information. That might actually be more useful in your particular situation rather than knowing the standard deviation of all of the classrooms about the grand mean. The other thing I can do then is I can use margins to plot each of these, and I can see that the teacher three's overall mean is the highest and teacher two's is the lowest. And if I treat them as fixed effects in the model, I could even include interactions, such as things like not just which teacher is it, but teacher experience. So then I can start putting things in the model, like interactions or other teacher level variables that take into account features of the teacher or the classroom in addition to features of the student. So there are other ways that you can talk about this. Okay. So that's what I mean by fixed versus random. If you're estimating a standard deviation for that clustering, that's treating it as random. If you're estimating a separate mean or moving it over onto the fixed side of the equation, that makes it a fixed effect. And mathematically, they are equivalent. I can't emphasize that enough. If you just sit and work it out, I guess I should add a slide in here that makes it more obvious. But grand mean plus each deviation is beta 1, beta 2, and beta 3. So that fixed part is equivalent either way you do it. It's just a matter of how you interpret it and how you would set it up. Okay? So I think, well, we have 3 minutes. Let me zoom through a couple other things. We could do this for binary outcomes. So let's say we used pass, fail. If we had a binary outcome, we could set it up the same way, except we would use the me-logit command. We would get odds ratios from this, and that makes a big mess. And I'm not going to talk about the odds ratios, or the syntax looks pretty much the same. But what we can do is use the margins command to convert those odds ratios to the predicted probability of passing, and then plot those for each teacher. We can fit cross-classified random effects. So we've pretended that the students were nested within the same teacher classroom every year. And we all know that never happens. That's completely fake. What happens in real life is that the clusters change from year to year. Even if you had the same group of students in a school, they're going to get rearranged in teachers' classrooms. And there is a way to deal with that. It's called cross-classified random effects. So the nesting structure is changing from year to year, and it's just a simple change in the syntax. At the teacher level, you would put underscore all colon r dot teacher, but the output ends up looking the same, and the interpretation is pretty much the same. Finally, if you wanted to do a Bayesian version of this, let's say you prefer using Bayesian methods as of state of 15, you can just type Bayes colon. Oops, I'm sorry. Oh, I
I
thought there
think
was a
you're good. I
question.
think it was a mistake.
Okay. If you wanted to fit a Bayesian version of this model, you could start by just typing Bayes colon in front of your mixed command, and that will then report the means of the posterior distributions, the standard deviation of your posterior distributions, equal tail credible intervals instead of confidence intervals. So just by typing Bayes colon, Stata, we've already picked some default priors for the parameters and things in there for you, and you can customize those if you want. But that's an easy way to get started using Bayesian methods if you want to just type Bayes colon in front of mixed or whatever regression command you're using in Stata. Okay. So I've got lots of videos. Those videos I mentioned are linked here in the slides. I've written blog posts about this, as well as how to do power calculations for these, because you're going to have to do that using simulation methods. So if you need to do power calculations for multi-level or longitudinal models, this blog series ramps up to that. So in part 4, I talk about how to simulate power for multi-level and longitudinal models. So if you need to do that, that's all in a blog post. Whoops. So again, you can download all the materials here at tinyurl.com/multilevel behavioral. Feel free to grab the slides and the do files and distribute them, use them however you like. No copyright from my point of view. And I'm not in any hurry. I'm happy to hang out and answer more questions, but if you think of them later, you can shoot me an email at chuber@stata.com. So thanks again for being here. Thanks, Jordan, for setting all this up. I know this is a lot of work, organizing and sending out all the invitations and setting up the Zoom links. So thanks again for being here.
Thank you so much, Dr. Huber. I'm seeing the chat that a lot of people have really benefited from this, whether they've taken multi-level yet or as a primary to multi-level. I know for me it was an amazing refresher that, like I said, I think I got even more out of it having already taken it and kind of
Yeah.
refresh. And now I'm like, oh my God, that's what was happening. happening. So I'm so glad that we had you
Yeah.
because it helped me. I know that.
Well,
With
thanks.
that
I'm glad.
being said, yeah, I see some awesome reactions in the chat. Um, yeah, some people who are in Dr. Rambo Hernandez's class that are excited for your talk in a few weeks now that they've heard you here. And so with that, if y'all have any additional questions, like Dr. Hooper said, you can email him directly off the slides, or you can send them my way and I can compile them. Whatever works best for y'all. Oh, I do see one question. Dr. Hooper, do you have your own YouTube channel about stats instead of just data cores?
I did. So I used to be faculty at A&M years ago, and I was chasing tenure. I did eventually get tenure, but while I was chasing tenure as a junior faculty, that's why I set up my own YouTube channel, was mostly to get the students. Because when you're a professor, if those of you who are faculty, you get the same question 10 times in a day, and it's just not efficient to have students dropping by your office and you explain the same thing 10 times in one day. So I started a YouTube channel with just frequently asked questions, things that I knew I was going to get questions about. Um, but when I moved to Stata Corp about 13 odd years ago, I took down my channel and now I just populate the Stata YouTube channel. But there are loads of videos, and there's also about 350 videos. The Bayesian videos are very popular if you're interested in learning about Bayes and MCMC. Those are very popular. But there are about 350 videos up on the website, and I'm currently working on a companion website to go with each of the videos. So each video will have a companion little written section as well. So you have the code, and I write out some descriptions and some of the math. So I don't have my own anymore. I took it down over a decade ago, but the State of YouTube channel is fairly it's got a lot of teaching stuff on there too. So
Yes, I see. The person who had asked was looking it up in real time as you were explaining it, and they said they see the videos, and thank you so much.
sure, sure.
I'll leave just a couple more minutes because I know for me, sometimes I need to digest for a second and then figure out how to phrase my question, especially if it's on a topic that I don't necessarily grasp 100%. So I'll stay on
Sure.
for a couple more minutes if any of you want to hang back and ask a question or two. But if you're all set, then I want to thank you so much for joining us. And we hope to see you next semester. We'll have a whole new set of speakers and topics. And thank y'all for joining us. Bye.
Bye. Thanks again.
Thank you, Dr. Huber. Thank you, Jordan.
No problem. A lot more thank yous in the chat. I'll stay on for a couple more just to make sure.
I'll go ahead and
Oh, I
paste
had a
that link
question
in.
I wrote down actually.
Okay, sure.
Um, so you know how in your slides where you had showed all the normal curves and like who they belonged to. My question was, say that the observation, the Yij that we were looking at the whole time that was towards the right of the line, say they didn't
Uh-huh.
belong to teacher two, but instead they belonged to teacher three, which was on the far right. Would their values just be negatives then?
No, they would be deviating from a different teacher mean. Um,
Mm-hmm.
Let me share the slides again and I'll show you what I mean.
Sure.
So let's see. So many slides. Yeah, so
Yes.
this observation here is
Mm-hmm.
deviating from this particular student mean. But
Mm-hmm.
if it was a different, if it came from a different student, then that observation might be over here and deviating from this particular student mean. I don't know if you can see my
But
cursor
I
moving
guess what
around,
I'm
but
saying is like we were treating that student and their set of observations for the teacher in the middle. What if that student
oh,
belonged to the teacher on the right?
oh, then it would be negative. You're right. Yeah. So if
Okay.
they belong to the teacher on the right,
Mm-hmm.
then those values would be negative. So it could be a combination of positive and negative. Um, I chose this student intentionally because they were all positive, because it's
Sure.
easier to think of something plus something plus something plus something. But you're exactly right.
Mm-hmm.
If it was on the left side of the mean, it would be negative. So, and they all could be negative in theory. Something on the left side could just
Mm-hmm.
as easily be, if it was the first teacher on the far left, it could be the classroom to the left of that and an observation to the left of that, in
Sure.
which case they would all be negative or some mix and match.
Sure. So I'm
Well,
guessing then, like, if it was like that, then the blue arrow would be just really long, and then we'd have some negative in the other color arrows, and that would still make your equation.
exactly.
Okay.
Let me, because I can show you a concrete example of this. Uh, not here we go. So here is I actually do this, and in the do file it has how do you generate these random effects for you. It's easy to do. You just have to know the commands. So this is not the deviation. This is the actual UI for teacher 3. So the
Mm-hmm.
UI dot dot for teacher 3 everywhere in the data set is 0.7. Well, it happens to be positive. The student effect for this student, that UI dot IJ dot, that's 3.78 for this student. But notice their residual is negative because the earlier ones were on the left side of the mean. And so they are negative.
Got it.
Because in order to have that mean, some of them, if they're bouncing around zero, some of them would have to be negative and some would have to be positive.
Mm-hmm.
So yeah.
Awesome.
So yeah, some can be negative, some can be positive. But it's interesting that in the software, you can actually see what are those actual effects. And there are things called caterpillar plots that some people like to do to see which, if you have a lot of clusters or a lot of students, or maybe you have 20 or 30 teachers, you can actually generate these effects and then plot them in order to see which classrooms tend to be higher or lower. So even if you treat teacher as a random effect, you can predict that random effect and then plot them or summarize them and see which teachers tend to have higher deviations and which have lower, and which direction and all that. So this is just barely skimming the surface, but yeah.
Awesome.
Yeah.
Thank you so much. Again,
Sure.
that was so extremely helpful. And I just thank you for taking the time out of your day to come and speak to us and help us understand this topic that you happen to be an expert in. We're really appreciative.
Well, thanks, and happy to do it again anytime. Just let me know.
Awesome. Thank you so
All right.
much. With that, I'll be
All right.
logging off. Bye,
All right.
guys.
Bye.